Hey, welcome back. In this video, we're going to continue looking at the Biot-Savart Law. All right, let's look at an important example, and that is to use the Biot-Savart Law to find the magnetic field due to a straight current-carrying conductor of finite length. So just a straight wire. We're going to find the magnetic field. All right. Well, the first thing I might want to do is orient this wire in space somehow. So what I'm going to do is put the wire on the z-axis. You don't have to put it on the z-axis, you can put it on any axis. You should put it on an axis though, that makes the calculation a little bit better. So we'll put the wire like this. And we're finding the magnetic field due to a finite length wire. So here's our wire. And you might ask, well, how can that wire just begin and end like that? Yeah, so in reality, it can't do that, right? It has to have a return path. So maybe that goes off in the positive or the negative x direction, like into the page, and then it just kind of comes back out at us for just this little segment. So this is an approximation of a situation that you might see in real life. So here's our current carrying wire, and we're going to say that it begins at A and it terminates at B. All right, now what we can do is find just a little piece, a little chunk of that thing, like that, and that's what we're going to call dl. And dl is going to be in the direction of current. So it's that direction there. Now, we're going to talk about a field point, but we're not going to choose any specific field point. We're going to just pick a generic point like that because we want our answer to be general. And then what we do, and this is kind of the same process that you saw for Coulomb's law, we're going to locate the field point with a vector. We're going to call that vector r. And we're also going to draw we're going to keep the figure simple like that for right now. Okay, so I've oriented the conductor along the z-axis. That was my choice. I've identified a differential element in the wire, dl, and I just kind of picked that. We're going to integrate over the wire in a little bit. And then I've chosen a point P, call that a field point. Okay, and the vector r locates P from the differential element dl. So this is a line of current, and so the Biot-Savart law says that the small magnetic field due to that small piece of wire is given by this thing. Okay? Now, I'm going to use cylindrical coordinates here, and you'll see why I'm using cylindrical coordinates when we get to the answer, because I know how the magnetic field behaves due to a current carrying wire, and after this example you too will also know how the magnetic field behaves due to a current carrying wire. So I look at dl and I ask myself, well, what is changing in dl? So if we go across, if we traverse that little infinitesimally thin segment, then the only thing that's changing is the z coordinate. So dl in this case would be dz in the z direction, like that. And I'm also going to need radius vector r, so I can figure that out by starting at my infinitesimally thin segment and going to the field point, P. So notice if I do that, I have to go rho in the rho direction. That's nice because we oriented the wire on the z-axis. So I go out in the xy plane rho in the rho direction, and then I go down the z-axis by z. Or you can call that z prime. Maybe we should call that z prime. I'm just going to leave it as z. I introduced the prime coordinates at the beginning of electrostatics, just to keep it simple as you were developing this theory. But I think that you should understand the process now. I'm going to leave off the primes. Okay, so again, just to get from dl to our field point, we have to go down by z, and then we have to go out from the origin by rho. So now, according to the Biot-Savart law, the small magnetic field due to this wire is given like this. Over 4 pi, and then the length of this vector r is the square root of rho squared plus negative z squared, and then I take that to the third power. So that's because I have a square root and to the third power, that's like to the 3/2 power. Again, we saw something similar with Coulomb's law. So it's this now that I have to compute. All right, now let me work on that numerator. Let me work on that cross product. So I have I dz in the z direction. So let me set up my cross product. So I'm just going to handle that for right now. So this is I dz az cross rho a rho minus z az. So I'm going to compute this cross product in cylindrical coordinates, of course. So this is, I need a rho up here, I need a phi, a z, this is 0, 0, and then I have I dz, and then a rho, 0, negative z, like that. Okay, so I compute that cross product, and I get I rho dz in the phi direction. So I'll trust that you know how to compute that determinant, how you compute that cross product. Okay, so that is the magnetic field due to just that little infinitesimally small segment. Now what we have to do to compute the entire magnetic field at that field point is integrate our result there. Remember, the numerator was this thing. Then we still have the denominator, 4 pi rho squared plus z squared to the 3/2 a phi, like that. Okay, now we saw an integral like this for Coulomb's law, and the trick was that we are going to let these kinds of integrals come up a lot in electromagnetics. We're going to let z equal rho cotangent of, not phi, theta. And z, so we're doing a trigonometric substitution here. So when I take the derivative, then dz would be negative rho cosecant squared theta d theta. And the reason I do that is because when I make that substitution, I'll have something like this. Negative I rho squared cosecant squared theta d theta. Right, so here I've put in, for dz, I've put in negative rho cosecant squared theta d theta. And then in the denominator, I have 4 pi times, and I'll factor out a rho squared. Then I'm left with 1 plus cotangent squared theta. There's something really satisfying about these types of integrals. I love these, trigonometric substitution. All right, now I can apply a trigonometric identity in the denominator. That 1 plus cotangent squared is cosecant squared. So I'm going to leave the numerator alone for right now. Notice I haven't put any bounds on my integral yet because I'm still kind of finagling it a little bit. I'm doing the substitution. So this becomes rho squared cosecant squared of theta to the 3/2. That's why you make that substitution in the first place, so you can get that nice property. And then in the denominator we have cosecant squared then to the 3/2, so that makes cosecant cubed. Same thing with the rho, that makes rho cubed. And so then I have rho squared over rho cubed, which is 1 over rho, and then cosecant squared over cosecant cubed, which is 1 over cosecant, which is sine. That is awesome. So this gives us negative I over 4 pi rho. I can take rho out, and I'm left with sine theta d theta after the substitution, like that. All of that is just that nice now. So we can certainly integrate that. And I'm still leaving off the bounds on purpose because I need to get back z's to put some meaningful bounds in there. Okay, so I integrate sine, I get negative cosine, so the negative goes away. And now I need to put z's back. And to do that, I draw a right triangle. And you can set up your right triangle however you want, but pick one of the non-right angles to be theta. And we said that z was equal to rho cotangent of theta. So cotangent is adjacent over opposite. So I need something like this. I need whichever angle I picked, I need the adjacent to be z, and I need the opposite to be rho, so that when I do cotangent of theta, I get z over rho. And that makes the other length then the square root of z squared plus rho squared, right, in our right triangle. So now if I want, so that was based on this definition, right? I chose that. So now if I want the cosine, that's adjacent over hypotenuse, right? So that makes the cosine of theta z over the square root of rho squared plus z squared, right? So now I'm in business. Now I have I from my integral, I over 4 pi rho, and then cosine is this z over the square root of rho squared plus z squared. And now I'm going to figure out the bounds here. Now that I've got z back, I say, okay, well the z's go from A to B. A to B, and then I'm in the phi direction. And so then when I plug in the bounds, it's very simple. I can't really get a number, you know. I don't really want to get a number, but I can't simplify it anymore because I don't have any numbers. And I get this. So that's my result. That is the magnetic field at any point away from the wire. You tell me B, you tell me A, you tell me rho, and then I can tell you what the magnetic field is. Now, I want to point out the direction of the magnetic field, because again, the direction is probably the trickiest part. Notice that our answer is in the phi direction. So let us think about that for a second. Pretend that you are standing atop the z-axis and you're looking downward. What you would see then is that the wire is coming out at you, like the current is coming out at you, and so we represent coming out at you with this dot inside a circle, like the vector tip is coming out at you, and that's dl. Okay, and then if you're looking down, then here's your positive x-axis, and here's your positive y-axis, like this. And your field point you see somewhere in space, you know, this point P right there. And so you have this vector, right? And that was rho. That was the distance away your point P is in the xy plane. So that's rho. And then this is the phi direction, right? And so this thing would sweep out an arc like that. And so you look down, And so our magnetic field was in the phi direction, so that is precisely tangent to the curve like this. So that is the direction of H. Alright, right in the phi direction. Now, I chose cylindrical coordinates ahead of time because I knew what the result would be. It's that the magnetic field swirls around the wire. So swirling around is good for cylindrical coordinates. And how I know that is because I did the right-hand rule ahead of time. The right-hand rule, you can arrive at the answer in two separate ways. Number one, the kind of the traditional way is point your fingers of your right hand in the direction of the first vector, which is the length of the wire. So in this figure here, the second figure that I've drawn, that would be coming out at you. So now your fingers of your right hand are pointing right at you. Then you curl your fingers in the direction of R, or the vector that locates the field point. So now with your fingers right at you, you curl them towards the field point, and your thumb is left in the direction of H. So if you did that correctly, your thumb should be pointing in the direction of this red vector there, H. That's the traditional way of doing it. Another way of doing it that's helpful for magnetic fields, since they end up swirling around the wire. What you can do is, alternatively, point your thumb of your right hand in the direction of current flow. So in my second figure here, you would point your thumb out at you, and then your fingers, then you curl your fingers, they're swirling in the direction of H. So if your thumb is pointing out at you, your fingers are curling this way, and that's exactly the way that H goes. And at this point then, H is going like, your fingers would be pointing that way. Okay, so those are two handy ways of arriving at the direction of the magnetic field. Very important that you nail that direction down. Okay, now I just want to talk about some specific cases with our result. Here's our result of the short wire. Now if we had a semi-infinite conductor, let's say A is 0 and B goes to infinity. That's a common case where we start the wire at the origin and we let B go to infinity. In that case, our results, well, A is 0. When B goes to infinity, this is like B over B. I'll let you think about L'Hopital's rule there. And so our magnetic field for a semi-infinite conductor is just this thing here. For a semi-infinite conductor. Now for an infinite conductor, and we've talked about what it means to have an infinitely long, conductor. That just means the dimensions of the conductor are longer than any other relevant dimensions in your problem. So now if we consider when A goes to infinity and B goes to infinity, okay, this becomes B minus A. Let's see. Oh no, this becomes a B over B minus A over A, but then we also have the row there. So this becomes A goes to minus infinity, excuse me. If A goes this way and B goes this way, so this would be 1 over 1 plus 1 over 1. So that would be 2, and that would cancel with a 4, so we would have the magnetic field intensity due to an infinite conductor is this thing here. And again, I'll let you work that out on your own as A goes from minus infinity and B goes to infinity. All right, I think I have one more video on the Biot-Savart Law. So let us take a look at, again, another special important application.